Yeah, the heading today is Special Tools and Cost-Effective Solutions. The Komet Group is doing around 50% of all our activities are concentrated on special tools. What I like to do today, I like to give you a brief overlook about things, what we do. When we talk about special tools, we talk many times about high volume production. And this high volume production are very often aluminium components, and therefore we are working many times with PCD type inserts. Unfortunately, a PCD type insert, you can see it here, is a brazed PCD blank, which is mounted on a basic carbide insert. And here we have the problem that long chipping is what happens many times. So, and our task is now to do a good chip control and a chip forming. And this chip forming we are doing by chip forming geometries. As you can see here, one version will be chip forming by doing a ground chip breaker, or the other version will be a chip groove, and we do this by laser cutting, by laser printing. The result will be a controlled and short broken swerve, which is a basic requirement for all high volume production for a stable process, and the chip and the swerve should not destroy the production. Yeah, how do we do special tools? First of all, the designer will have the component on its screen. This will be an example, a motor housing. And then the next step, he is now deciding what kind of inserts do we need. Do we do a roughing operation? Do we do finishing? And then he decides, okay, in here, for the center boring, we go for carbide inserts. And for the outer diameter, we go for PCD inserts. The basic reason for that will be a very low cutting speed for the inner inserts because it's a small diameter, and a very high cutting speed for the outer inserts. It's a question of tool life and sometimes also of chip control. Yeah, this is wrong here in this position. Next, for doing a controlled cut, even in such a complicated form like a combustor area in a cylinder head, you can see that we can do PCD inserts by wire cutting in each certain profile what is required. Such kind of components you can find in 3-4 million pieces a day. So tool life is a very important issue here, and also process stability. Another kind of tools I like to show you are so-called hybrid tools. So what is a hybrid tool? Everybody knows a hybrid engine. You mixed fuel engine in combination with electric energy. But if we talk about a hybrid tool, we talk about tools which is doing different kind of machining process combined in one tool. This could be milling, backspot boring, drilling, grooving, and in this case you find a milling section here as well as here. Here we do face plunging and boring, and the front tool, unfortunately you can't see it completely here, it's a thread milling cutter, and we start with drilling a core hole, followed by the thread milling, and followed by chamfering, and this is all combined on one tool. Such a rear axle housing, or a rear axle from a passenger car, which is fixed together with different components. So we have some welding connections here. You can see an Audi turning tool, which is now machining this bigger end on such a rear axle. And such a tool, you can see it here, is not made in one piece. It's very often made in 2 or 3 pieces. Otherwise, it will not be possible for manufacturing, because inside you can find a lot of inserts and also on the outer diameter. And some of these inserts will have a directly adjustment here by a small wedge screw to set the tool onto a finished diameter. Another hybrid tool you can see here. It's a PCD boring and milling tool. See the different diameters, 94.8, and cutting speed of more than 2,500 meters. I hope the noise will come also. You see the tool running here, and on the front you also can find a drill. It's a simple indexable insert drill which is mounted just on the front to save some space in the tool magazine, to reduce numbers of tools. And now you see the tool running. Just straight in circular milling for doing the serration profile. And again, the serration followed by a simple drilling operation, which is cutting down the time dramatically. So we don't need a tool change time and so on. Another nice tool, when we talk about special tools, you see such a VABOS system. VABOS means variable boring and sinking tool. And on this combination, what you can see here, we have a very small thread milling cutter with a serration profile, a S80 into a pitch of 3 millimeter. The bore diameter is roughly diameter 80. And the component is a filter housing. You can find this on each truck where you have an outside housing, and inside you have a filter bush. And this is connected directly to the engine. And it's a really a challenge to do such a component, the total component, including the thread milling, in 8.8 seconds. The whole tool is equipped with PCD blades, and tool life of such a milling cutter or such a boring tool will be roughly 400,000, 500,000, 600,000 components with just one tool. Aluminium housings like gearboxes or clutch housings and such components, when they come to the machine, they are pre-machined just to make it possible to clamp it in the fixturing. But very often you can find bores which were shown on the drawing as an open bore, but on the end of the day the bore is closed. And this was an experience what we make exactly on this component. The preferred tool was just for boring, and now we have to put a drill here on the front just to get through the bottom, on the closed bottom, and this combination is saving also another tool change, and is saving downtime of the whole machine. A manifold housing, it's a part of the cylinder head where you can find the thermostat bore. It's very typical in such components where you can't machine from the front or you can't machine it from the rear side. So you have to enter the bore from this side, from this direction. And you see it's with the eccentric design. So the tool is fixed, the spindle is orientated, you move to the side, you go forward, you come back to the center, and then you do a backspot boring. The tool itself is making a finished diameter, so it's an H8 class bore here, and therefore we have also a small adjusting cartridge or an insert seat with an adjustment screw. The whole tool, because of the long tool overhang, it's a question of the rigidity and stability, will be made from heavy metal. You will say, HSK and heavy metal, this doesn't match. You're right. So the back part here is from steel, and this heavy metal part is shrinked in up to here. So the rest is like a spring steel, what is normally suitable for HSK adapters. A combination tool with Audi turning, grooving, plunging, and backspot boring, you can see here, and also the task. So first of all, we enter the whole tool with an offset to get the front part through the bore. We come back to the center, we're machining the backspot boring, and then we just move straight forward and machining the front face of the tool, of this component. And then we exit the tool on the same way. So spindle orientation, lift off, and getting out of the hole. These all were aluminium components. Another nice tool from cast iron, you can see here. We do here ID turning, 41.5, 49.5, and so on. We do OD turning, we do circular milling, we do drilling and thread milling, all in one tool. And I'd like to show you a short video about this tool. So the tool comes in, starts with the center hole, machining on the center position. Then the OD turning starts, face plunging. Then we have to change the spindle speed because now we have machined all the big diameters. Now we change the gear and we're speeding up the spindle for a circular grooving, internal grooving. Then we speed up again for drilling the core hole of this M4 thread, followed by a thread milling operation and chamfering of this thread. Such a hybrid tool saves normally or combines normally up to 10 kind of tools in one tool. This is very simple in cast iron because chip control is not so important. Cast iron will give you automatically a short broken chip. It will be more complicated if you're machining a soft kind of aluminium or a long chipping material maybe from steel. Another challenge will be reaming operation here in the cylinder head. This is not just a short reamer, it will be a quite long reamer for the whole camshaft seat. And here we have two versions which were very common. One version will be an ideal entry. So the entry face will be straight. Sometimes it's already machined. And a difficult situation you can see here on the right side where the cap of the camshaft will be much wider than the aluminium cylinder head itself. So it's very difficult for a reamer to enter into the bore under such a condition. So what do we do first? We have a pilot reamer for the first journal, for the first hole. And this pilot reamer will have a special front cutting geometry. This front cutting geometry is not with 90 degree, it's even a negative angle, just for a good centering of this pilot reamer. It should not shift away, it should not be pressed to the side. And with this reamer, we're doing first a pilot bore, followed by a 45-degree angle for machining the finished diameter. The next will be a long version of reamer. And with this long version, you can find here on the front the same head, what we have already in use here on the pilot reaming tool. And then we move into the first journal, and with these guide pads and some exit holes for the coolant, we will guide the reamer and we will finish all the other journals step by step. The multi-flate principle of such a reamer, which will have 6 or 8 cutting edges, it depends on the diameter, and the benefit here will be a very high linear feed rate, up to 1.5 meters or more. Yeah. Modern engines are working or are built out of different kind of materials, like the CGI material, this vermicular graphic iron for cylinder blocks for the common rail, or modern diesel technology. And here you can find, or you can see a component. It's a fuel engine or a petrol engine. Sorry, a petrol engine. And here we have the challenge that we have to machine 2 different materials at the same time. So one material will be cast iron. You see the crankshaft cover will be cast iron, and the housing itself, the whole block, will be from aluminium. And normally you're using PCD for aluminium, and you're using a coated carbide for the cast iron part. But what shall we do now? We have both at the same time, and this is the challenge here. When you look on such a component, you have this cast iron, mostly in a coated version, and you have the aluminium part, what you normally machine with PCD. And here you can see the cutting speed. And there is a certain overlapping area. In this overlapping area, you can machine aluminium, you can machine with PCD cutting material, also cast iron, and you can do it the same with coated carbide in a higher range or in the highest range of cutting speed. And we have to work in this overlapping area. So the perfect cutting material for both aluminium and cast iron is not existing at the moment. And as long as this is not existing, we have to do compromise with the cutting parameters and with the cutting edge geometry to get a good surface, to get a straight hole, to get good cylindricity, all this demand tolerances what we have on a cylinder block. You can see it here once again. Here we have the tool rotation, the cast iron cap and the block itself. The problem will be in the radius we will have the material overstand. That means the difficulty in the entry. We have tool deflections. We have a problem maybe with chip forming in the aluminium part. And in the intermediate section, this will be exactly here. Here we are changing all the time the cutting condition. Aluminium with the easier cut, and cast iron where we have more and higher cutting forces. So this makes vibrations coming up when we change, when the insert or the cutting edge change from one material into the other. So from the surface finish, there's a negative influence by small vibrations coming up. And also these vibrations we have to keep low, or we have to eliminate the vibrations by a good guiding of this reamer. A reamer system will look roughly like this. We have the basic adapter, we have a runout and angle correction system here to keep the reamer exactly straight. Then we have here on the integral tool, we have guide rails to keep the reamer straight in the bore. We have setting blades, and we have on the front part 4, 6 cutting blades, what we have to set on diameter and what we have to set on the angle, the back taper of these guides. What you can see here, this is not a guiding blade, this is just to set the measurement equipment, where I can have the reference size of my dull indicator. Yeah, this is normally 20 microns below the original diameter of the reamer. My last 10 minutes, I like to have a focus on so-called mechatronic tools. This, we call it Comtronic tools or UX systems, are boring heads or generating heads, which makes you able to make each certain contour in a machining center. Different heads are existing here. So what is a UX system? What is a UX system doing? At first, we can do a linear interpolation in the machining center, in a standard machining center, or we can do also a circular interpolation in a standard machining center. And that's new. We don't need a special machine which is connecting the boring head to a drawbar system or to a rotary drive system to make such kind of contours. Valves, bearings, molds. So all different contours possible to machine this on a machining center. Very, very popular at the moment is doing such turbocharger for passenger cars in a machining center. This has to be done normally in a turning machine, and all the other milling operation and drilling operation have to be done on another machine in another setup. And now we save the setup by doing all this contour machining, all the diameter machining, now in one setup in a simple machining center. I just look for the interest parts. You can see here the trumpet bore in the center. Move just a little bit forward. And once again, We start with the facing operation, and this radial slider in this UX system, in interpolation with the set stroke of the machine, makes it possible to do all the different contours in a tolerance of 3 to 4 microns. With the head, which have the biggest stroke, smallest strokes, we have a setting accuracy in 2 microns maximum. Yeah, another example for Formula One engines builders or test fields where we do valve seat generating with such a head. You see here the relief chamfer followed by the valve seat and by the second relief chamfer. And these angles could be changed easily just by changing your program data on your on the machine panel. See here, intake and exhaust with one tool. These are different diameters, different sizes. We just move the slider to the another position and we start again the program. Here you can see also the automatic tool change, because the cutting speed is very low. We are machining here a component from a nuclear power plant. It's Inconel 725 on a DMG machining center. See here now the tool which comes in from the tool magazine, moves down to the component. And what we are doing here, cutting speed of about, which is very low. I think it was about 30 meters, 25 meters. Yeah. Then we have a rough cut and we have a finish cut. And what we're doing here is a very high precision angle. So the spindle moves forward and the slider moves inwards. And this is exactly in the end result an angle in a tolerance of 23 degrees, 0.152 degrees. You see how the whole system is now working completely under the water, more or less under the water. And it's made for through coolant as well as flash coolant from outside. It doesn't matter. It's completely sealed, so it runs very safe. Another component which was very common to machine this on a machining, not on a machining center, but on a special machine, is a differential housing inside the spherical seat. This spherical seat is also very accurate, and we do this today also in a machining center, including all the other operations like drilling and face milling. Now the boring tool goes in through this small center hole, and then we do this facing operation here again by a radial and axial interpolation of the machine axe and the axe of the cylinder of the tool. My last example, what I like to show you here with a so-called UX system. You can see here the smallest one, what you have seen right now, but also bigger systems are existing, and such tools were in use in big diesel engines, from steamers, from big earth movers, 16-cylinder V. Now the machine is coming with a spindle in a pickup system, because the tool changer will not be able to carry the weight of this tool. It's a big gantry milling machine. See also the component. See also the operator next to the machine, just to get you a little impression about the dimensions of such a component. And right now, with an interpolation, the machine moves under the angle of the V-block engine and an angle into the bore. What we are doing now with our boring tool, there are 2 sliders mounted, and these 2 sliders are machining now the water jacket, the water clearance inside. We are machining all the accurate seats and the balcony seat, which is very important on such a component. On the tool itself, we have also fixed mounted insert cartridges and insert blocks, and we can change the tool from roughing into finishing just by changing a quick change by HSK connection or ABS connection. These front tools, and also the front tools which are mounted on the sliders here. And then the tool is suitable very quick for two different operations. One is roughing, one is finishing, and all the contours inside could be easily modified by small changes in the CNC program of the machine. Yeah, that was a rough overlook about our special tools, what we do, what is our daily business. And I'd like to say thank you for your attention.